since we know, we need to find out what is our where my open loop zeros is going to be placed. Then the next thing we need to do is to use angle criterion. Because we use angle criterion, if we put a pole somewhere, all the open loop pole location, all the angles between the closed loop pole and the individual open loop pole and zeros, they must be negative 180 degree. That's a rule we learned in rule locus. So that is a way we determine where I'm going to put my zero, because at this moment I don't know where my zero is going to be located. Now, we're going to use angle criterion, which means does that make sense? So I have a few things. The first one is, this is easy because I know this one is 45 degrees. So over here, this one must be 135. Second one is this one. Which is also pretty straightforward. Let's talk about this one as, let's use, what did I use? No, I use V. Just use theta. So theta is going to be tangent 6/2. Everybody understand what I'm doing? This is triangular relationship. I know this is 2, I know this is 6. So 6/2 is going to be arctangent theta. So if you do something like this, this is going to be 70 something. So this angle over here is going to be 180 degree minus theta. That is going to give me 108.4 degree. So I find out the two angles over here. However, I have no idea where this one is located, but it doesn't really matter. Because how many zeros I have in this system? Just one. So I only have one VZ minus 135 degree minus 108.4 degree. What does this equal to? Negative 180 degree, which means VZ is going to be 63.4 degree. So far, any question? Pretty straightforward, right? I'm not using anything special we never done before. It's just angle criterion, and everything starts from the concept of rule locus. So once this one is done, we are looking for, do I have anything with water? So I need to have a zero somewhere. What is the angle over here? This one, right? So do you know where this one is going to be placed? You do, right? Because this is vertical divided by horizontal. Vertical is 6. Horizontal is going to be, let me put Z minus 6. The reason I put 6 is because it's projection on the horizontal axis, so this one must be negative 6, right? So over here, I'm going to get Z is about which means the open loop controller I have no is going to be this one. So far, any question? What is the next thing we need to do? Determine what? Okay. So what are we going to do? What are we going to do with this one? The next thing, in order to determine K, is determine controller and K using what? We have used angle criteria, so what is the other one we need to use? We talk about two different criteria, as well as magnitude criteria. Very good. But how are we going to use that? Before I move to this step, any question so far? Is that straightforward? So I have identified my open loop poles and zero. Then I need to make a way to ensure it's going to attract it by these two, to those two positions. That's a goal. So what does this mean? It means that my characteristic equation configuration. So when we do something like this, it means that when I put absolute value, what does that mean? Distance. That's engineering mathematics. Do not tell me you don't learn this before. Okay. When we say the exponential thing, phi is the angle we're talking about. When we are talking about the arc, that's the radius. So when I'm talking about the arc over here is the distance between this guy and the closed loop pole. Open loop pole to closed loop poles. Open loop 0 to closed loop pole. It doesn't matter where you put it. The thing we're worried about over here is the distance. So, in other words, I think I made some mistake. It should be not by 4, right? Let's close loop 4 constant over here. So 4K. I'm not going to put absolute value over here because K is a constant, and we never had negative feedback, negative gain in our system. That is going to be S plus 4, S plus 9. Okay. Next thing we need to figure out is what are those absolute value is going to be look like. So we got 3 distance, this one, and this one. Yellow. So this one over here is going to be 6 squared plus 6 squared. The distance over here is going to be 6 squared plus, I should use 2 first, 6 squared. This one over here, since I put my pole around 9, so this one over here is going to be 3 squared plus 6 squared. So far, any question? Should be pretty straightforward, right? Nothing difficult. And I believe all the calculation I'm doing right now, you guys learned that in high school. So in other words, automatic control is nothing more than high school concept, right? Everybody has high school diploma, should be able to learn this class. And you guys are Tsinghua, so you are much better than me. I believe that. Yeah, seriously. Okay, so I got this one, so just put the number into this thing. I get 8.5, which is this one, or this one, 8.5, sorry, 8.5, 6.3, 6.7. So I'll have 8.5 multiplied by 6.3 divided by 6.7. Keep in mind on the other side that's 4K. So it yields K equals to, this is about 8. So K is about 2, which means my controller is going to be 2s plus 9. That ends my design of the controller. Next step. Write your answer with the correct form. Any question? So this is just the framework. How we can design a controller based on what we have learned. We start from S-plane because we need to identify where we want to put our closed loop poles. Then after we put our closed loop poles, we start to determine what we want to do because we might need to use PD controller, we might need to use PI controller, we might need to use PID controller, or you guys really crazy, you want to use multi pole location somewhere, that's fine. Just put all whatever you want to do on the S-plane, okay? However, keep in mind you need to do dominant pole location. Other than those two, anything must be faster than those two. It must be on the other side. Once that is done, based on what you have decided, whether it's PD, PID, whatever, PIID, PDD, whatever, then you just put it over here. Determine your desired pole locations. Then you start to use angle criterion to figure out where you're going to put your poles and zeros. Then once this part is done, then use angle criterion, well, magnitude criterion to determine what is a K going to look like. Then that is your answer. Any question? The only thing that doesn't make sense over here is, okay, in this problem, I know I only have a single zero. But if I have two things, one pole, one zero, what happened? Because over here, we can figure it out easily. I know my pole, and I know my closed loop pole, and I know there is only one variable, single configuration, one unknown. We can figure it out. What happened if we got 1 0 and 1 pole in this system? What are you going to do? Any suggestion? You got two variables you need to design, but you only have one S point. So what are you going to do? Any suggestion? Come on, be creative. The answer is pretty easy. The answer is, I don't know. What are we doing? We are doing what? Controller design. When I say design, what does that mean? You put anywhere you want to. But keep in mind, you still need to fulfill the criteria you want to do. So you got one, based on what I'm showing you, how many unknowns you can deal with over here? 1, 2, 3, or 5? Just one, right? So you can just design all the others, then put something over here to fulfill everything. Is that valid? Yes, it's valid. However, it might be a little bit painful because we say we're going to design. That really, when you design something, it's really based on your experience. So you can say, okay, I want to, if you have pole and you have a 0, you can say, I want to put it somewhere over here, or over here, or somewhere crazy. It will turn out you can never fulfill the criterion even though you put your 0 somewhere. You try to compensate that, but it won't happen because you choose the wrong position of the poles. Okay? So only when you put your poles at the correct positions, then it will save you a lot of your time. If you don't put those things over here, because you can tell me, okay, I have one here, and I want to have 2 poles and 1 0, or no, 2 poles and 3 zeros over here. So I decide I would like to put 3 poles all located at 0. That is fine. But how are you going to arrange the locations of the other zeros? That will be something you need to worry about. And as I said, this part over here can only deal with one unknown, which means you need to design the other 2 locations of your zeros. You only have 1 0. So where is the best place to put those things? That will be somewhat a little bit painful to determine. I have one homework problem. I don't know whether I should give that to you. It looks straightforward, but we spent about 12 or 14 hours to tune the place, to tune the position. It's just painful. It looks pretty straightforward to second order system, but you need to spend like 18 hours. No, some people spend like 2 nights and they never figure out what's going on. But some people is lucky, they just put it somewhere quite close to the position, and everything is going to be solved. So it's really bet on your luck. 你们现在用语叫做要赌人品，对不对？ Do you want to have this kind of problem as your homework? 你们可以看自己的人品好不好。Now that's really creative because nobody really know it's going to be that difficult. Even the professor who designed the problem, so we should be able to solve that in about 20 minutes. But it turned out to be 10 hours. So he just next week he just told us, why don't you tell me it's so difficult? 谁敢去说 That's the thing. Any question? I still have 5 minutes left. I'll stop right here because I don't have enough time to finish the next example. But next example is that the question I have for you guys, what kind of controller I'm designing over here? What is the problem of this one?
Too fast.
Huh? No, not too fast. What is the problem of a PD controller? Is this a proper controller? Do we have any poles in this system? When we say whether the system is implementable or not implementable, it means that my order in the zeros is higher than the order of the poles. It is not implementable because we are predicting future. We are using future information to design the controller. So over here, we have 1 0, but we do not have any pole, which means this one over here is not implementable. So PD controller is a pretty bad idea. Well, though I don't agree with that. If you are using digital stuff to implement this thing, it's okay. But traditionally, we do not like PD controller a lot. So we need to use, at least in order to use PD, because PD is a good thing, we can limit the overshoot and make the damping ratio smaller and meanwhile it's fast enough to compensate for everything. So we like PD controller, but we do not like the truth that it doesn't have any pole. So in that case, we would like to use something we call lead leg controller. This one has a specific format, just like what I said. We like to have PD, but we also need to have a pole. So we can just put this guy over here far away and use this part to design the controller. Does that make sense? So as long as this one is far away, we'll be okay, because it is no longer non-feasible, non-implementable. Meanwhile, we still keep the convenience of a PD controller. We can still reduce the overshoot, increase the damping ratio, everything good is still in the same place. So next time when we come back, we're going to talk about, this is called lead leg controller. That is something we're going to do. Just keep in mind, you just have your controller like this, but it's going to increase another pole, which is far away. If you are too lazy to design everything, you can just put your S equals to, the pole location equals to 1,000 or 100. It's still the same, because it's still on the other side, negative 180 degrees. But we're going to talk about more realistic calculation of everything next time. Any question? Is that understandable? Why we want to have a lead leg controller with one pole and one zero? Okay. You guys have a nice weekend.